what if everything we thought we knew about the universe is about to change? So in the most recent episode, Joe Rogan sits down with astrophysicist David Kipping to explore the deepest mysteries of space and time, from galaxies that seem too old to exist, thanks to the James Webb Space Telescope's shocking new images, to the possibility that aliens are watching us right now. This conversation will blow your mind.
One of the most pressing things, one of the reasons why I wanted to bring you in, because you are very knowledgeable in all things space, is the James Webb Telescope and all the different stuff that they've been finding, particularly about these galaxies that were formed very shortly after not within our lifetime shortly, but cosmologically shortly after the Big Bang, that it seems like we have to figure out why these things are forming. Is the universe older? There's all this different kind of speculation. Maybe the Big Bang is not 13 point whatever billion years old, but maybe 22, 24. Like, what is your take on all this?
Yeah, the James Webb Space Telescope is such an incredible instrument. The data has just blown us away. You know, when you build this thing and you look at it unfolding in space, you think there's so many ways it could go wrong that we all were just like, you know, I think it was 215 moving parts or something had to unfold. So, you know, just the fact the fact it just all worked was just remarkable.
Right.
And then when we got those first images, they just kind of blew us away as well, because we had sort of these engineering expectations of what it would do, but the data was just even better than that. So when it, you know, of course, the first thing you want to do is point it to the most distant part of the universe and see what's out there in those darkest patches. And so when it did that, it started finding a couple of things. It started finding quasars, which are kind of the center of these very active galaxies. These are supermassive black holes that have loads of crap falling in, and they're spewing out all this energy. They're kind of feeding supermassive black holes. And so we started detecting those way earlier than we thought the universe should be able to build them. Because to make a supermassive black hole, I mean, these things are like 100 million solar masses. Imagine that, 100 million suns have not only been born but died, gone through their entire life cycle, died, collapsed into a black hole, and then those black holes have presumably somehow merged together into this super behemoth of this 100 million solar mass thing. So we're finding those just, 300 million years after the Big Bang. And that was like, hold on, that doesn't make any sense. Like, how can this be? And similarly with the galaxies, we were seeing these images, these galaxies, and you can date roughly how old they should be based off the redshift. So the universe is expanding. So therefore, if something is very far away from us and the universe is expanding, its light gets stretched more and more and more as it journeys over space. And so we can use that redshift to kind of date how old these things are. When we use those dates, we look at these images, again, they seem suspiciously too old. You really shouldn't be able to form these things that early on in the universe. And so that kind of puzzled us. I think for the galaxy thing, there's a bit of a resolution there. One of the resolutions is that we probably miscalculated how easy it is to form these galaxies in the first place. So we had these models for galaxy formation, we had these models for how stars should form, how quickly they should live, but it was all essentially calibrated on what we see around us, like right here in this part of the universe, in the local universe. And then we kind of realized that those same models probably need to be tweaked if you're going to apply them to the early universe, where the density is so much higher, the gas temperature is much hotter, everything's just completely different in the early universe. So when you kind of make those corrections, it actually looks like maybe it's actually possible to make those galaxies earlier than we thought. So I think the galaxy problem is a bit easier to explain. I think the quasar problem to me is more interesting. How do you get those supermassive black holes so early? There's a certain kind of maximum rate you can feed these things called the Eddington limit. And that's sort of you throw mass into a black hole and so much energy is going in, some of it spews back out. And the energy which spews back out stops other stuff coming in. Right? So there's a maximum limit. You can't build a black hole faster, in principle, than this Eddington limit. And yet, when you do the calculation, these black holes must have been fed what we call super Eddington. So faster than Eddington. So something's wrong with our models, right? Either we've got the universe age wrong, which I think is possible, but I would say that's probably a much less likely solution, or we've got the astrophysics wrong.
Why do you think that the universe's age is a less likely solution?
Because we've got this, like in particle physics, you've got the standard model, which includes like all the particles and the electron, the baryons, all these kind of stuff. And in cosmology, we have a similar kind of model. It's called lambda CDM. And so the lambda stands for dark energy, and the CDM is cold dark matter. So this is our standard model, and we have used it to explain so much stuff in the universe, Joe. I mean, we're talking about the cosmic microwave background, oscillations in the sky, these baryonic acoustic oscillations, the stretching in the universe, Cepheids. You can use it to explain so much stuff, and it works beautifully. I mean, it works down to like the 0.01% level. So if you say the universe age is wrong, you have to give that up. So maybe it is wrong, but if you give that up, you have to come up with a radical new idea, which can now explain all of this stuff at that same level of precision. The much more likely answer, in my book, is that astrophysics, like the gas swirling around, the plasma colliding with each other, that's just more complicated in my mind than the actual model of just the simple expansion of the universe, which actually is a fairly simple geometric model.
Fairly simple in that you can use whatever methods that we're using currently to measure everything that's out there, and it makes sense.
Yeah.
But if we're using something like the James Webb Telescope, so we're getting a much deeper view of the universe, how limited is the James Webb in comparison to James Webb 2.0, 3.0? Like, are we going to have to continually revamp what our understanding of this process is?
Yes, we will. And that's
exciting.
That's what I love, right? That's
Isn't that
what scientists love. Every time we've built a telescope that is, 10 times more precise than the last thing, every time we've done that, we have been surprised. And so these early galaxies are a good example. The cosmological experiments that are going on now, one of the big surprises is this thing called the Hubble Tension. Have you heard of that? Hubble Tension? So Hubble Tension is measuring the expansion rate of the universe. How fast are things flying apart? And you can do it two ways. You can use the cosmic microwave background. So that's the earliest radiation that we can detect. This is that stuff that's about 3 Kelvin warm. You can detect in the microwave. And this is the light which has traveled basically when the universe was 380,000 years old. It's that light, and we see it in all directions. That's how we know the Big Bang kind of didn't happen in one place. It happened everywhere, because you just see this light coming in from all directions. And from studying that radiation, you can kind of get a model of the universe, and then you can calculate, using this model, how fast should the universe be expanding today if I run the clock forward. And you get a number. And then if you do that same experiment but locally, you actually measure the stars. You measure the supernovae around us, these pulsating stars, and you actually measure how fast this stuff expanding, you get a different number. They don't line up. And so this is really weird. So somehow something's wrong, right? Either our measurements of the local universe must be wrong in some way, or this model that we're using to calculate the whole history of the universe, something is wrong with that model. So this is a very famous growing problem in cosmology. It's now what we call a 5 sigma level. So that means the chance of this being random is just like 0, essentially. It's just this is a real effect. And now we just have to figure out who's wrong. Is it the observers or is it the theorists?
Wow. Where do you fall on this?
Yeah, it's hard. I swing between both ways. I'll talk to my cosmology colleagues, and they'll, depending on who I talk to, they'll convince me either way. So I think
that's disturbing that people are convinced. If these new telescopes keep showing us this new puzzle, it always bothers me when someone is like rigidly convinced.
Everyone has a certain pet theory, right?
Bias.
They're trying to push. We all have biases, right? Yeah. So
human beings.
Yeah. I mean, it's hard, right? If you've spent 20 years of your life, most of your academic career, studying this one thing, it's really hard to turn around and say, you know what, I screwed up. Right, that's 20 years of measurements, they were all wrong, and I have to eat humble pie.
So what do you guys think? Is our universe older than 13.8 billion years? The James Webb Space Telescope has been out there for almost 3.5 years now, but it's been revealing stunning details of galactic collisions and newborn stars hidden in cosmic dust. It's making discoveries that no one thought we'd see so soon. If this is what Webb has uncovered so far, and this is how confused we are now, what will it find in the coming year? Could the next big revelation completely rewrite our cosmic history? I'll see you guys in the next video.